Alright everyone, so I am actually re-recording one of my earlier reviews, the first one that I did. The audio in the recording was, I guess, messed up, and so I'm going to try to re-record that review, alright? So I'm going to cover the same topics I did. I might be doing slightly different examples with different numbers. But for the most part, it's the same as what I covered in my first review. So the first thing that I wanted to talk about was the cross product. And I'm not going to spend too much time on the cross product. It seemed like most people were already comfortable with the cross product. So I'm just going to do a quick example of how to compute the cross product, and I'm going to mention its most important properties. Okay, so if I have two vectors, A and B, let's do an explicit example. So let's just choose a vector A. Let's make A the vector 1, 2, negative 1. And then let's choose another vector B. And let's say this vector has components 2, negative 1, and maybe positive 1. Okay? So if you want to compute the cross product of A and B, we usually compute the cross product as a determinant. So what you do is you put the vectors I, j, k in the first row. And then we're going to put A in the second row, B in the third row, and then the way computing this works is I'm going to start with I, and what I'm going to do is I'm going to cross out the row and the column containing I. So after crossing out the row and the column, take the remaining entries, and what you're going to do is you're going to multiply across diagonally, so 2 times 1 gives me 2. And then you're going to do the same here, minus 1 times minus 1 is a positive 1, and you're going to subtract that. So you're going to do this times that, minus this times that, okay? That gets you the first component of the cross product. Now for the next component, you're going to minus. So you always do minus for the second one. And then similar, cross out the row and the column containing j. And then do the same thing, 1 times 1 is 1, minus, and then here negative 1 times 2, so minus and negative 2. Okay. And then the last one will be plus, and then k. Again, cross out the row and the column containing k, and then do 1 times negative 1, minus 2 times 2, so minus 4. Okay? Alright, if we put that all together, we have 1i. This is minus 3j. And then minus 5k. Or if you prefer, we can write it as vector 1, minus 3, and minus 5. Okay? So I think most people know how to compute the cross product, but I just wanted to do one example in case people were still struggling with that. So what I want to go over is the most important properties of the cross product. Okay? Let's zoom out. Okay, so perhaps the most important property is that the cross product of two vectors will be orthogonal to both of the vectors that were crossed. So if you will, A cross B is going to be orthogonal to both A and B. Okay? And you can verify that in the earlier example. So remember that two vectors are orthogonal if their dot product is equal to 0. And so if you do A dot product with A cross B over here, okay? So doing the dot product will be 1 times 1, and then plus 2 times negative 3, so minus 6. And it'll be plus negative 1 times negative 5, so plus 5. And so indeed the dot product is 0, and I won't do it, but you can check for yourself pretty easily. Dot product between B and A cross B should also be 0, okay? Alright, so the cross product of A and B is orthogonal to both A and B. Okay. That is probably the most important property of the cross product for us. I'll mention a couple other properties. So the magnitude of the cross product is equal to the magnitude of A times the magnitude of B, and times the sine of the angle between the two vectors. And this happens to be equal to the area of the parallelogram determined by the vectors A and B. Okay. Third property that I'll talk about is, second property shows you the magnitude of the cross product. Regarding the direction of the cross product, the direction is determined by the right-hand rule. Okay. All right. And so I will try to demonstrate that. But right now I don't have a camera that will work very well. So I'm going to try to add in a video about that later on. Okay. I think that's all that I really wanted to mention about the cross product. And for us, again, I think the most important property of the cross product for us is property number 1, okay? So again, the cross product is orthogonal to both of the vectors that you crossed, okay? All right, so the main topics that I really wanted to go over for this review are lines and planes. So I'm going to start by talking about lines. In particular, lines in 3 dimensions and lines in R3. Okay. Alright, so in 2 dimensions in R2, or in the xy plane, we represent lines with an equation. Okay. So standard form was y equals mx plus b. That's the slope-intercept form for the equation of a line. Okay. In 3 dimensions, we represent lines a little bit differently. So we don't use an equation involving like x, y, and z as one might think. I'll kind of talk about why we don't do that later in this video. But for now, regarding how to describe a line in R3, okay. Okay, so in order to describe a line, we're going to need 2 pieces of information about the line. So first we're going to need a point that lies on the line. I'm going to call that point r subscript 0. Okay. And then I also want a direction vector, which I'm going to call v. And this direction vector should point along the same direction as the line, if you will. Or maybe I should say the direction of the vector should be pointing along the line. That's slightly more proper. Okay. So with these 2 pieces of information, I'm going to define a function. Okay. And so it's a function of the variable t. And I'm going to define this function r0 plus t times b. Okay. So this function, we typically call this a parameterization. Of a line. Specifically, it passes through the point r0. And it is parallel, or yeah, I would say parallel to the vector v. Maybe I'll say, and it is along the direction v. Okay. And as for how this parametrization works, the way that I like to think about it is we know that when we take a vector v and we multiply it by a scalar, all that does is it stretches the vector or shrinks it and possibly reverses the direction. So if you consider all scalar multiples of some vector v, that is essentially going to give you a line that is along the direction of the vector v. However, this line that we get always passes through the origin, because when t is 0, you get 0, okay? So if I want the line to pass through the point R0, I just need to translate it by adding R0 to everything. And so that's how we get this equation for the parametrization of a line. Okay. Now, this is also, I think, referred to as the vector equation of a line. Okay. And so referred to as a vector equation because, of course, in the formula, it involves a vector v, and also we have the point R0. Okay. And just like a really simple example. So if I imagine the line in R3 passing through the point let's say the point 1, 2, 3, along the direction of the vector, let's do maybe 2, -2, 4. Okay. All right. Okay, so if I wanted to represent this line in R3, okay, then I can represent it using this function, this parametrization, RT equal to. So I'm going to take the point R0, 1, 2, 3, and then add to it t times our vector 2, -2, and 4. Okay? Alright. Now, if I were to do the vector algebra here, adding the x components together, we get 1 plus 2t. And we get 2 minus 2t. And then we'll get 3 plus 4t. Yeah. Alright, so then this would be one way of describing this line passing through the point 1, 2, 3 and along the direction 2, -2, 4. So basically, for each possible value of t that you can plug into this function, that's going to give you a point on this line. Now, there are a couple other ways that we can describe a line in 3 dimensions. So from the parametrization, and if I use this example here, from the parametrization, if you read off the x, y, and z components, in this example we have x was 1 plus 2t. We have y is 2 minus 2t. And then we have z equal to 3 plus 4t. So this set of equations is often referred to as parametric equations. So you can see these are the parametric equations of our line. Okay. So in the parametric equations, you can see how the point and the direction vector appear. So the point 1, 2, 3 appears as these numbers out here. The direction vector, its components appear as the coefficients of t. Okay. By the way, the variable t is usually referred to as the parameter. Okay. And so parametric equations are another way of describing a line in 3 dimensions. In general, okay. If you want to describe the line passing through the point R0 and along the direction V, okay. So if the components of R0 are X0, Y0, and Z0, and if the components of V are A, B, and C, then the parametric equations for the line will be given as x equals x0 plus at, y, its equation would be y0 plus bt, and for z, its equation would be z0 plus ct. Okay? Alright. So that's kind of two ways that we can describe a line using a parametrization. Or if you look at the components of the parametrization, you get the set of parametric equations to describe the line. Okay? Now there's a third way of describing a line in 3 dimensions, which I personally don't think is too important, but we will mention it. So if you take the parametric equations and if you solve for the parameter t in each of those 3 equations, okay? In the first equation, we're going to get, if we solve for t would be x minus 1 over 2. The second equation, t would be y minus 2 over negative 2. In the third equation, we would get t equals z minus 3 over 4. Okay? Now, because these 3 equations are all equal to t, that means that they are all equal to each other. So you can write it as x minus 1 over 2 equals y minus 2 over negative 2, which is also equal to z minus 3 over 4. So this set of equations is referred to as the symmetric equations. Of the line, okay? And again, keeping track of how the point R0 fits into the equations, and how the direction vector 2, negative 2, 4 fits into the symmetric equations. So this time the direction vector, its components appear in the denominator of the symmetric equations, while the point, its components appear in the numerator. Okay? Alright. So in general, for the symmetric equations of a line, okay, If the line passes through this point, x naught, y naught, z naught, along the direction v, components a, b, c, the symmetric equations are going to be x minus x naught over a equal to y minus y naught over b equal to z minus z naught over z. Okay? And then combining that with the parametrization, or the vector equation of a line. So parametrization, aka the vector equation. Which took the form of a function r of t equal to r naught plus tv. So these are the three ways that we have of describing a line in 3 dimensions. Okay. All right. Okay. All right. So then these would be the 3 ways of describing a line in R3. Okay. All right. So let's work through another example. Okay. All right. So suppose we have the line passing through the points let's see here. Let's see, passing through the points on -2, 3, 0, and also the point let's do 3, 1, -2. Okay. All right. So we have 2 points, and so of course between any 2 points there should be a line connecting the 2 of them. And we want to find the parametrization of a parametrization of this line, as well as the parametric equations, as well as the symmetric equations. Okay. All right. So in order to get the parametrization, or really to get any of these, what do we need? We need a point on the line, which I called R naught. Okay. And right now in the problem, we're actually given 2 points on the line. So we definitely have a point on the line, so that's good. What we also need is a direction vector for the line. and we are not given that. All we're given are these 2 points on the line. So we need to use the information that we were given to come up with the direction vector. Okay? Alright, so that's pretty easy to do. So given the 2 points, what we can do is find the vector between those 2 points. That vector naturally lies along the line, and so we can use that for our direction vector. Okay? Okay, so to get the direction vector, we just want the vector connecting our 2 points. Remember, we get that by subtracting one from the other. So I'm going to take the point 3, 1, minus 2, subtract the point negative 2, 3, 0, and that gets us our direction vector. Looks like it'll be 5, negative 2, negative 2. Okay? Alright. So we have a direction vector now. For the point, we have 2 points given to us. We can use either of them. Let's just use the first one, negative 2, 3, 0. Okay? So with these 2 pieces of information, we can now write out the parameterization, the parametric equations, and the symmetric equations of this line. So we'll start with the parameterization. Okay, so the parameterization is the function r of t equal to r naught, so negative 2, 3, 0, plus t times v, so v was 5, negative 2, negative 2. Okay? Alright, so that's the parameterization, or the vector equation of our line. To get the parametric equations, so remember the parametric equations you can basically get by reading off the x, y, and z components of the parameterization. So the x component is negative 2 plus 5t. And then y is 3 minus 2t. And then z is 0 minus 2t. Okay. Alright. And then finally, for the symmetric equations, so remember that you can get them just by solving for t in the parametric equations. So in the first equation, solving for t, we'll get t is x plus 2 over 5. In the second equation, if we solve for t, you would get t as y minus 3 over negative 2. In the third equation, if you solve for t, you're going to get t as z over negative 2. And because these are all equal to t, you can set them all equal to each other, and that gets you the symmetric equations, alright? And so again, that's 3 different ways that we have of describing a line in 3 dimensions. Okay. Alright. Now I do want to mention real quickly, so you've kind of seen how to, from the parameterization, get the parametric equations, and from that get the symmetric equations. So it's worth noting that you can always work backwards as well. So certainly if you have the parametric equations, you can write out the parameterization. Basically, you know that this is the x-coordinate in the parameterization, this is the y-coordinate, this is the z-coordinate. To go from the symmetric equations to the parametric equations, that's pretty simple as well. So I'll just illustrate with this example how to go from symmetric to parametric. Okay. All right. So starting with the symmetric equations, you just take each part of the equation, set it equal to t. And then if you just solve for x, y, and z, you will recover the parametric equations. Okay? All right. So from parametric to symmetric, you solve for t, and then equate those equations to each other. To go from symmetric to parametric, you take each part of the symmetric equation and set it equal to t, and then solve for x, y, and z. Okay? Alright, so that's all that I'm going to say about lines for now. I'm going to move on to the subject of planes in R3. Okay. So we saw that for lines, we can describe them using a parametrization. Alright, so we need to know how to describe a plane in R3 now. Okay. Alright, so for lines, we needed two pieces of information. We needed a point that the line passes through, and then we needed a direction vector telling us how the line is passing through the point. Okay. So for a plane, we also need two pieces of information, or rather, we are going to use two pieces of information to describe a plane. So again, we're going to suppose that we have a point R0, which lies on the plane. And then instead of having a direction vector, we're going to have a normal vector to the plane instead. So by normal vector, we mean a vector perpendicular or orthogonal to the plane. So let me draw a little picture of this. So let's suppose here we have our plane. Actually, I'll make a slightly bigger picture. Alright, good. So there's our plane. We have this point, x naught, y naught, z naught. And then we have this normal vector, which I'm going to draw attached to this point. Okay. So if I take any other point that lies on this plane, let's say I'm going to take a point out here. It's with some coordinates x, y, z. We can form the direction vector connecting our 2 points. And because this vector lies in the plane, the normal vector should be orthogonal to it. Okay? That holds for any point on this plane. And the idea is that a point will be on the plane only if the direction vector connecting it to this original point is orthogonal to the normal vector. Now, for two vectors to be orthogonal, their dot product has to be 0. So we can say n, the normal vector, which is components a, b, c. And then dot product with this direction vector connecting our 2 points, which remember you get by subtracting the points, so it would be x minus x naught, y minus y naught, and z minus z naught. These two vectors should be orthogonal precisely when x by z is in the plane. If they're orthogonal, then the dot product should be 0. Okay? So this gives us an equation for the plane. If we actually multiply out the dot product, we'll get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Alright. So that gets us the equation of a plane. So this is the equation of a plane passing through the point x naught, y naught, z naught. With a normal vector with components at a, b, and c. Okay? Alright, so it's worth noting how the point and the normal vector appear in the equation. So the normal vector essentially comes from the coefficients of x, y, z. The point x naught, y naught, z naught is being subtracted inside these parentheses. Now, if we rearrange this equation a little bit. If we distribute the a, b, and c, we're going to get ax plus by plus cz. We also have the minus ax naught, minus by naught, minus cz naught. So if I move all of that stuff over to the other side, and if I just replace all of that with another letter d, so d would just represent everything that was on the right hand side. This is another way of representing a plane. Okay. Now I don't like this equation quite as much. I think the first equation is better because it's a bit more explicit in how the point plays into the role in the, or I guess the point is more transparent or explicit in this equation up here, whereas it's sort of hidden in this equation because it was all put into this variable d. Okay? Alright. So we'll do a couple of examples finding the equation of a plane. Okay, so let's say we want to find the equation of the plane I'll start with maybe this example first. So I want the equation of the plane parallel to the plane 3x minus y plus 2z equals 4, and passing through the point let's just do 1, 2, 0. Okay. Okay, so in order to get the equation of the plane, what do we need? We need a point on the plane, and in this problem we are given such a point, so we have that information already. We also need a normal vector, which we're not given explicitly in the problem. Okay? So we need to use the information in our problem to come up with a normal vector. And so the idea is, in the problem there's two planes, so this is the plane that we are looking for. It is parallel to this other plane which is given to us. So from the equation of the plane that was given to us, we can read off a normal vector for this plane by looking at the coefficients of x, y, and z. So remember, the coefficients make up the components of a normal vector to the plane. Okay. So the vector 3, -1, and 2 okay, coming from the coefficients up here. That gives me the components of a normal vector to this plane. Because our two planes are parallel to each other, that means that this vector should also be normal to the plane that we are looking for, okay? So therefore, we can use this vector as a normal vector for our plane. So we have a normal vector now. So then just writing out the equation. So remember, the equation has the form a, b, c. Well, a times x minus x naught, b times y minus y naught, plus c times z minus z naught equal to 0. A, b, c were the components of our normal vector. X naught, y naught, z naught were components of a point on the plane. So I'm going to use the point of 1, 2, 0. Okay? So then that will give me the equation of our plane. Alright. If you want to, you can distribute the coefficients. So I will get 3x minus y plus 2z. And then move all the constants to the right-hand side. So here we get minus 3, which we would move over and it will be plus 3. Here you get plus 2, which when we move over will be minus 2. And then here that's 0. Alright. And so you can also rewrite the equation as 3x minus y plus 2z equal to 1. Alright? So these would both be acceptable answers in this example. Alright, so for the rest of the review, I'm just going to be doing more examples of getting equations of planes and maybe a few about lines as well. Alright, so let's try doing another example. So let's say we want the equation of the plane. And this time what we know about the plane is that it contains a line described by this parametrization. Oh, I'll write it like this. Okay. Alright, so we know the plane contains this line. And let's say we also know that this plane contains the point. Let's do 2, 0, and 0. Okay? Alright. Alright, so again, in order to get the equation, you just need two pieces of information, a point on the plane, and again, we're given a point on the plane already. You also need the normal vector to the plane, which we do not have at the moment, alright? So most of the problems about finding the equation of a plane boil down to using the information given to come up with a normal vector. So let's see how to do that in this type of problem. So I'm going to draw a picture. Here's our plane that we are looking for. There is a line on the plane right now, so let's pretend that's the line on the plane. And then we also have a point on the plane. Let's suppose that point is out here. Okay. All right. Now, from the parametrization of the line, we know that there is a point on the line. We can get the point by looking at the constants, 3, 0, 1. So this is a point that lies on the line. We can also read off a direction vector of the line from the coefficients of t. So -1, 2, -4. Okay. All right. So let's call this point A. Let's call the direction vector V. I'm going to call this point B. All right. So if I label them in the picture, let's say, so this would be A on the line. This would be the direction vector V. And then this would be the point B. So in order to get a normal vector to the plane, what we can do is get the direction vector from A to B. So then that will give us two different direction vectors on the plane. And if we compute their cross product, we know that their cross product would be perpendicular to both of them. And to be orthogonal to both of them, it would have to be orthogonal to the plane. That's the idea. Okay? Okay, so we're going to get the normal vector by taking the cross product between the vector AB as well as the vector B. Okay? Alright, so the vector AB, we get it by doing the point B minus the point A. So if we do B minus A, that's going to give us, let's see here. Alright, so B minus A would be 2 minus 3, it's -1. 0 minus 0 is 0. 0 minus 1 is -1. Okay. So we're going to do the cross product. IJK. And here is vector AB. Here is vector V. Computing the cross product. So we're going to get 0 minus a negative 2, so positive 2, times I. Next is minus. And then we're going to get 4 minus positive 1, so that'll be 3j. And then it's plus. And then we're going to get negative 2 minus 0, k. Alright, so we got the vector 2, negative 3, negative 2. Okay? Alright, so now that we have the normal vector, remember that gets us a, b, c. And then for the point on the plane, we'll use the point 2, 0, 0. So that gives us x naught, y naught, z naught. And then writing out the equation of the plane, so it's going to be a times x minus x naught plus b, which is actually minus 3, times y minus y naught being 0. And then this plus c, so minus 2, z minus z naught, which is 0, equal to 0. Okay? Alright, and if you simplify that, you can get 2x minus 3y minus 2z. And moving the constants over, the minus 4 becomes a plus 4 on the other side. And these are 0, so that would be it. Okay? So then each of these will give you the equation or an equation describing the plane. Okay? Alright. I have time for one more example, probably. Before that, maybe if I can just touch on one thing. So as I mentioned earlier, most examples involving finding the equation of a plane boil down to using the information given to find a normal vector to the plane. A very common strategy for finding a normal vector to the plane is if you can get two direction vectors on the plane, you can just cross product them to get the normal vector. Okay? Alright. So I have time for one more example. Well, maybe two more, I don't know. I have quite a few examples, so I'm just deciding which one I want to use. Okay, I'm gonna do this example. Alright. So let's suppose I'm given two planes. Let's say the first one is given by this equation. And then for this one, let's do x minus 3y and let's do plus z equal 1. Okay, we'll try that out. Okay, so we're given these two planes. Now, in 3 dimensions, any two planes are going to intersect in the line. So here I'm trying to draw a picture illustrating. Alright, so for any two planes in 3 dimensions, assuming they're not parallel, they are going to intersect in a line, alright? So what we want to do is we want to find the line of intersection between these two planes. And to find the line of intersection, that means we want to find at least a parameterization of it, or a set of parametric equations, or a set of symmetric equations. So we'll probably just get the parameterization of it. Alright? Now there's a couple of different ways of approaching this problem. Let me try to illustrate 2 ways to go about this, alright? Alright, so this first method, this is more of a sort of purely algebraic method of coming up with a parametrization for the line of intersection. So the strategy is to set one of our variables equal to t, and then solve for the others in terms of t. Alright, so to illustrate this method, set one variable equal to t. So I'm going to just set z equal to t. Okay? So then in my equations, we're going to have x minus 2y plus 3t equal to 3. And then the second one is x minus 3y plus z equal to 1. No, I'm sorry, and z is t, so I'm going to plug that in for that. Okay. And what I want to do now is solve for x and y from the system of equations. So I think the simplest way to solve it would just be to subtract these equations right now. That will cancel out the x's. We're going to get minus 2y plus 3y gives me 1y. 3t minus t be plus 2t. Here 3 minus 1 gives me 2. So therefore we have y equal to 2 minus 2t. Okay? Now to solve for x, we can substitute this back into either of these equations to solve for x. I don't think it really matters, so I'm going to sub into that first equation. So in the first equation we had x minus 2y, which I'm going to replace with 2 minus 2t, plus 3t equals 3. And so this is x minus 4 plus 4t plus the other 3t gives me 7t. So solving for x will give me 3 plus 4 will give me the 7. And then we're going to have minus 7t. And then we had z equals t from the beginning. This will give you a set of parametric equations for the line. Alright. So of course you could get the parametrization or the symmetric equations from that, but I'm just going to stop with those parametric equations. So that's one method of finding the line of intersection. Now there are, I would say, lots of different things you can try to do to get the equation of the line. There's a way of getting the equation by thinking a bit more geometrically about the problem. So I think I'll just illustrate another way to solve the problem. Excuse me. One which is more geometric. Okay. So the idea is, if we want to find a parameterization of a line, we know that we need two pieces of information: a point on the line, as well as a direction vector for the line. Okay? So let's think about how we can get these two pieces of information, alright? Let me take this picture right now, and I'm going to use it again. Okay. So let's think about getting the direction vector in particular at the moment. Okay, so we want a vector pointing along the same direction as the line of intersection. Now, since the line lies in both planes, that means this direction vector also lies within both of the planes. So therefore, this direction vector should be orthogonal to each of the normal vectors of these two planes. And so to get a vector orthogonal to the two normal vectors, we would just need to do the cross product of the two normal vectors, okay? So that's what we're going to do for the direction vector v. We are going to obtain it by getting the cross product of the normal vectors from each plane. Alright, so let's go ahead and do that right now. So here are the two planes. Alright. So remember that you can get the normal vectors from the coefficients of x, y, and z. So here, if I do the cross product, I'm going to get so the first normal vector, 1, minus 2, 3. Second one, we have 1, minus 3, 1. Okay. If I do the cross product, we're going to get negative 2 plus 9 will be 7. Next, we're going to have negative 1 minus 3. Right, so that's minus a negative 2. And last, we have negative 3 minus negative 2, should be negative 1. Okay? Alright. So we have a direction vector for our line. Okay. We also need a point on the line. So to get a point on the line, alright, so a point on the line would be on both of the planes. So to say that this point is on both of the planes would mean that that point should satisfy both of these equations. So point on the line, we can get a point on the line just by finding one point satisfying these two equations. Okay, so find point on line by finding a point satisfying both of the equations. Okay. Yeah, and so again, this point has to satisfy both equations because it must lie on both of the two planes. Okay. Alright, so in order to find a point satisfying both of the equations, we'll do something sort of similar to what we did above. What I'm going to do is I'm going to just pick a random value for one of the variables. Actually, let's do, so I'm going to plug in 0 for z. Okay? That will then give me the equation x minus 2y equal to 3, x minus 3y equal to 1. Now my choice of plugging in 0 for z is arbitrary. I could have chosen any other number. But I wanted to plug in a number for z. That way it would eliminate z from my equations, and then I'd be able to solve for x and y. Okay? And so that's what we're going to do. We're going to solve for x and y. So to do that, I can maybe just subtract as before. X's cancel, you get y equals 2. If we plug that into the first equation, get x minus 2 times y equals 3, until we get x equals 7. Okay? So then this point 7, 2, 0 would be 1 point that lies on the plane, or sorry, on the line of intersection, because it lies on both planes. So now that we have a direction vector, and we have a point on the line, we can write out a parametrization for the line, which I'll do over here. Alright, so remember the form, so r of t is the point r naught plus t times the direction vector b. So the point is 7, 2, 0. Our direction vector, we chose 7, 2, and negative 1. So then, not that it matters, but I'll just put it all together. So 7 plus 7t, 2 plus 2t, and negative t. Okay, so that will give us a parameterization of the line. You can get the parametric equations and the symmetric equations from that. Okay? Alright, so if we compare that to the answer from method 1, 7 minus 7t. So it's very similar. You actually notice that the signs are different though, because in the previous one we had 7 minus 7t, 2 minus 2t, and plus t. So that's okay. There is more than one parametrization of any line, so there's more than one right answer to these types of problems. Alright? So I think I'll wrap things up here. I ran a bit over time, so I'm just going to end the recording at this point. Alright, so thank you for listening. If you guys have any feedback, I would be more than happy to hear it. So I will leave my email in the description of the video. So if you guys want to send me some feedback, I would appreciate that.